Hello friends, in today's session we are going to explore some of the major signaling and monitoring systems used in Europe, focusing especially on the INDUSI system. These systems form the backbone of modern train protection and laid the foundation for the European ERTMS/ETCS signaling standard. Across Europe, many countries developed their own systems independently. Because of this, the continent now has a very diverse collection of signaling technologies, each originating from its national railway administration. Signaling systems in Europe. Historically, signaling systems evolved almost simultaneously across different European regions. However, since each national railway introduced its own design philosophies and technologies, Europe today has a wide variety of systems. Within Europe, three major areas of influence can be identified. Germany, which influenced countries like Austria and other Central European nations. France, which shaped signaling systems in Southern Europe and high-speed operations. The United Kingdom, those systems spread to many Commonwealth regions. Each of these regions developed their own unique concepts for train protection, communication, and speed supervision. INDUSI system. One of the most important traditional ATP systems in Europe is INDUSI, developed by Siemens. INDUSI is used extensively in Germany and Austria, and its principles are still in use today. The name INDUSI stands for Inductive Signaling and Control, and it is a point-based ATP system. This means the train receives information only when it passes specific track points equipped with beacons. History of INDUSI development. The development of INDUSI began as early as 1908, when engineers started searching for a reliable method of railway protection. Early prototypes required a continuous power supply to track-side beacons. This was impractical because electricity was available only near stations. At the same time, an optical communication system was explored, but it was abandoned because it required frequent cleaning of lenses, a serious disadvantage in real-world conditions. Finally, in 1931, Siemens introduced the first INDUSI prototype that did not require external power. It used permanent magnets and resonance-based detection, which made it far more practical. Development milestones. By 1933, engineers introduced a version based on resonant frequencies. This was a major breakthrough because it solved early detection problems, especially at higher speeds. From 1934 onward, INDUSI was installed across the entire German and Austrian networks and gradually spread to other countries in the German sphere of influence. Modern versions of this system are known as PZB, although the term INDUSI is still commonly used. System description. Now let us look at how INDUSI works. The system uses three types of track-side beacons, each tuned to a specific resonant frequency. These beacons are passive, meaning they do not require external power. All other processing equipment is located on board the train. The onboard system interprets the frequencies detected when passing a beacon and initiates warnings, speed supervision, or braking. Beacon placement. The INDUSI system uses three specific frequencies: 1000 Hz beacon, placed at the distant or advanced signal; 500 Hz beacon, located 450 meters before the danger point; 2000 Hz beacon, placed 250 meters before the stop signal plus overlap. Each beacon indicates a different level of caution or required response from the driver. The beacons can be activated or deactivated simply by using a relay linked to the signal aspect. System operation. When the train passes over a beacon, the resonance between the train's induction coil and the trackside beacon reduces the voltage and increases the current in the onboard circuit. The onboard INDUSI system interprets this as the detection of a specific beacon frequency. If the main signal ahead is red, all three beacons will be activated. At the 1000 Hz beacon, the driver receives a warning and must acknowledge it within 4 seconds. If the driver fails to react, the system immediately applies emergency braking. Once acknowledged, the train must follow a precise braking curve with strict speed monitoring enforced by onboard equipment. Speed supervision under INDUSI. In the case of fast trains, those operating up to 165 km per hour, the system requires the train to reduce its speed to below 85 km per hour within 23 seconds after passing the 1000 Hz beacon. These restrictions remain for at least 700 meters. After this point, the driver can press a release button known as German as the Freitest. In later generations of PZB, the restricted zone has been extended to 1250 meters to further enhance safety. INDUSI controls. This slide shows the typical INDUSI or PZB push buttons used in locomotives, including acknowledgement and release buttons. These controls are essential for driver interaction with the system and help ensure continuous monitoring of speed, braking behavior, and safe passing of signals. To summarize, INDUSI is one of the earliest and most influential ATP systems in Europe. It uses simple, reliable, passive beacons with resonant frequencies. Despite being developed nearly a century ago, its principles continue in modern PZB systems. The system played a major role in shaping later European signaling technologies, including the foundation for ERTMS ETCS. Okay, thank you.